Hi everyone, Patrick Orense here from PowerCrest, and today I would like to introduce to you this three-part video series I've made on transformers in parallel. Now, the topics I will be covering I have not seen covered in literature on power systems analysis. I'm sure they are covered somewhere, it's just I may not have come across it yet. Anyway, so the topics I will be covering in this three-part video series is Part 1, Mismatched impedances of parallel transformers. Part 2, Circulating current. And a question I will be addressing in this second video is if there is circulating current flowing between two parallel transformers, does the source know about it? And if so, how? So be sure to watch the Part 2 video if this question interests you. Part 3 is changing a transformer's vector group. The big question I will be addressing in this video is, can the vector group of a transformer be changed without opening the tank and physically rearranging the winding connections? Well, in short, the answer is yes. How? Well, be sure to watch part 3 of this video series. So let's get started. Okay, so to start off with, I want to look at what are the electrical requirements for paralleling transformers. The first one is matched impedance. That's the subject of this particular video, and I'll be looking at what is meant by matched impedance and what happens if the impedances are mismatched. Right, so the second requirement is identical voltage ratio. Here we'll be looking at what happens if the voltage ratios are not identical. That covers the whole subject of circulating current. The third requirement is identical vector group. And here I'll be looking at, as I've mentioned before, how can I change the vector group of a transformer without opening the tank? And the fourth requirement is same color. Just joking. Okay, let's move on. Right, here we have two transformers in parallel as our first scenario. 33 to 11 kV, T1 is a 10 MVA transformer, 5% impedance. T2 is 10 MVA as well, 5% impedance. Right, now let's calculate all our ohmic impedances at 33 kV. So we use the formula Z base is the voltage squared over the MVA, and we get that the Z base for these two transformers is 108.9 ohms. So the transformer impedance, or the ohmic impedance, is Z base times Z per unit, which is 108.9 times 0.05, which is equal to 5.445 ohms. Now please note that the transformers are usually mostly inductive. Well, inductive reactance, so we should use J. In other words, be doing complex calculations here. However, we will stick to real numbers to keep things simple, and it doesn't change anything to the bottom line of our results. So we can now represent T1 and T2 by their ohmic impedances as shown here. And we see that the current in transformer 1 must be equal to the current in transformer 2. So the load current, of course, being just the sum of the two transformer currents. And we can also see that the load current is shared equally between T1 and T2. So let's say rated load is 20 MVA, then the rated load current is 350 amps at 33 kV, right? So T1 and T2 will each have 175 amps flowing in them respectively. Okay, so now let's consider a situation where T2 is 5 MVA, still 5%. Right, now let's look at the ohmic impedances. Well, for T2, Z base is now 217.8 ohms, and we can calculate that the ohmic impedance is therefore 10.89 ohms. So we see that it is exactly double that of T1. Right, so representing T1 and T2 again by their respective impedances, we see T1 is 5.445 ohms and T2 is 10.89 ohms. Thus, The current in T1 is actually twice that of T2. Now we know that the load current, of course, is the sum of the two transformer currents. So we see that the load current is actually shared proportionally between T1 and T2. If rated load is 15 MVA, then rated load current is 262.5 amps at 33 kV, and T1 will carry 175 amps and T2 87.5. So we can say that T1 and T2 are still considered matched. Why? Because each is carrying their fair share of load current. Right? In a nutshell, if load current is 3 per unit, then in this example, T1 will carry 2 per unit and T2 will carry 1 per unit of the load current. Okay, I'd just like to briefly digress for a moment and discuss the subject of which percentage impedance do I use for a transformer which has different MVA ratings depending on the type of cooling. So, looking at this nameplate example, I have a nominal 45 MVA unit. The impedance is specified at 45 MVA, and in this example it is 9.15%. So the question is, if the transformer is designated as a 58 MVA unit and to be paralleled with other transformers, do I use 9.15%? For example, if I am going to use this transformer as a 58 MVA unit in my analysis software or in my calculations, and I'm going to parallel it with other transformers, what impedance do I use? Well, no, I do not use 9.15%. I need to calculate the equivalent percentage impedance at the new 58 MVA base, so I need a change of base. And the formula is percentage impedance new is the percentage impedance old times the change of base, and I get 11.79%, which, as you can see, is a 29% difference in the impedance value. So it is important to determine the equivalent percentage impedance at the base MVA to be used in the parallel transformer calculations. Okay, back to our discussion. Now let's look at the situation where T2 has an impedance of 8%, right? T1, 10 MVA, 5% as before. So now focusing on T2, we see that Z base is again 217.8 ohms, and that the impedance, the ohmic impedance of T2 is 17.424 ohms. Okay, so now we see that the impedance of T2 has gone up from 10.89 ohms to 17.424 ohms, a 60% increase. Right now, we said before, ideally, that the current should be split in a ratio of 2 to 1. So ideally, we'd like T1 to have twice the current of T2. But now we see that there's a bit of a mismatch, right? And we do a bit of the calculations and we see that T1 now carries 76.2% of the load current. And the balance, of course, is now taken by T2, which is 23.8% of the load. So the load current is now shared disproportionately between T1 and T2. T1 goes from 66% to 76%, which is about a 9.34% increase, and T2 goes from 33 to 24% of the load current. That is a 9.34% decrease. Well, what are the implications of this? Let's look at rated load current again, right? If it's 15 MVA, then the current is 262 amps at 33 kV. So now T1 carrying 76% of the load current will carry 199 amps and T2 the balance of 63 amps. So we see that T1 has now 11.37 MVA or 113.7% of its rated MVA, and T2 now carries 3.6 MVA, which is 72% of its rated MVA. So we can say that T1 had a 9.3 increase in its share of load current and 13.7% increase in MVA. For T2, we had a 9.34% decrease in its load current, but a 28% decrease in MVA. So T2 will certainly not be complaining about this situation. Okay, so what are the implications of all this? Well, we can clearly see that T2 is very happy, right? It's carrying much less of the load than what it should. The line share is really carried by T1, and T1 is now officially overloaded. So, remedy. What can we do about T1? Well, first option, leave as is. If T1 has sufficient cooling, or if the overload is only for a very short period of time, or if the ambient temperature is low enough to allow for the required cooling of T1, then nothing to do. The second option is to derate the system load so that T1 contributes at most 10 MVA, in other words, its rated power. Well, how to calculate the derating? We can go about it this way, right? Had T1 is 76% of the load current, which is 199 amps, but the rated current for T1 is 175 amps. So this calculation below results in the system now being derated from 15 MVA down to 13.16 MVA. So, in other words, if the system total load is only 13.16 MVA, then T1 will at most deliver 175 MVA, which is at its rated capacity. Okay, in summary, number one, matched transformers in parallel must have the percentage Z of each transformer being equal, regardless of the rated MVA of each transformer. Maybe if I can explain with an example to just make it a bit more clear. Let's say I have a 5, a 10, and a 20 MVA in parallel. Okay, this is just a theoretical example. You probably may not have such a situation, but just let's suppose for argument's sake that you have a 5, 10, 20 MVA in parallel. If the 20 MVA is a 10% transformer, then the 5 and the 10 MVA need to be 10% transformers as well. In other words, the impedance, the percentage impedance must be 10% for each transformer in that parallel group. This will ensure, of course, that each one contributes a fair share towards carrying the load current. Or you could say the load is proportionally distributed amongst those three transformers. Now, number two, ensure that the percentage impedance value used is the equivalent one commensurate with the MVA rating of the transformer. And this is applicable for transformers with multiple MVA ratings. So if I have a transformer which is, say, 10% at the rating of 20 MVA, and there is a rating given at 25 MVA as well because of additional cooling, then if I'm going to use 25 MVA in my calculations, I cannot use 10%. I would have to use the change of base formula and convert the 10% to the equivalent value at 25 MVA. Okay, number three, transformers with mismatched impedances, they may be parallel if the mismatch is not too large, but it does lead to unequal sharing of the load. Right, the load current will be disproportionately shared between the transformers in the parallel group. The transformer unfairly burdened may be overloaded and derating may be necessary. Okay. Now do note that mismatched transformers do not give rise to circulating current. Why? Well, see part 2 of this video series where I will address that particular question. Well, that's the end of part 1 in this video series on parallel transformers. Could I ask you to please share, like, subscribe, and comment. If you have any questions, please put them in the comments below. Thank you, and until next time.